Okay, this is video 6 in the series on review for test 1, where we're talking about op amps currently. And here we want to look at the last topic that we had listed in our list of things for op amps, and that is to derive transfer functions involving op amps. So let's consider some op amp circuit, and we'll just do something like this. These are really easy to evaluate, because if you simply replace the two canonic models of the op amp with or op amp amplifiers, instead of with an R1, R2, you just do Z1, Z2, right? Then you can write an expression VO. Instead of being minus R2 over R1, it's minus Z2 over Z1. And I guess I should really write this, I will say VO of S, like that. All right, and so now it's just a matter of finding what is Z1. In this case, it's R1 plus SL1. And what is Z2? It is R2 plus 1 over SC. Let's just take the subscripts off here to make it easier. Okay, and what's important though when you derive this is that you use a standard form. You know, put it in a good form. So I'm going to put over a common denominator, and now we're going to write the transfer function VO over VI is equal to minus Z2, which is SR2C plus 1 over SC, I'll put that down in the denominator, okay, divided by Z1, which is R1 plus SL. Okay, so now we have minus, let's see, we could write this as S over omega Z plus 1, and then here we could write this as let's see, C over R1 times S times S, so it would be SL over R1 plus 1. Actually, that's going to be, I take that back, S times RC. Yes, R1C. Okay, I'm trying to get it into this form where it's S something plus 1. Let me rewrite this one last time. S over omega Z plus 1 over S times S over omega P plus 1. And then this whole thing is going to be multiplied by, it looks like, 1 over, when we have actually S squared. I forgot that. Nope, no, we don't have S squared. I just wrote that twice. Yep. Okay, and then this whole thing is going to be 1 over, I'll call that omega 1. Let's leave that for the moment. Let's leave that. That'll be 1 over R minus 1 over R1C. So here we have to define omega Z. So omega Z is 1 over R2C, and omega P is equal to R1 over L. But I think I'll just leave it like this as a 1 over R1C. Okay, and the point is that it has two poles at the origin. So if we do a pole 0 plot, we would have a double pole at 0, and then we would have a pole at minus omega P, right? And then we would have a 0 at omega z, which I don't, or minus omega z, which of course could be to the right or to the left of the pole. And then of course we have a scaling. This is our scaling constant k here, which is not represented on the pole zero plot.